Hello, my name is Jawad Ahmed Fareed and I will be your guide in today's session. Today, what we're going to do is walk through the steps that are required in building a Monte Carlo simulator and then use that simulator to price simple vanilla derivative contracts, such as a European call and a European put option. Now, a natural question that you should ask is that if you already have the Black-Scholes equation for estimating the value of a European call and a European put, why do you need a Monte Carlo simulator? Why should we make the effort? The objective on our part is to build a simulator that we can use to price exotic contracts. But before we go to more complex, more complicated securities, it is important that our comfort with this simulator is reasonable, and that can only happen if we can reconcile and match the prices of simpler vanilla contracts using both the Black-Scholes equation and our simulator. The idea is that by the time we're done, you would know enough, or you would understand how to build such a simulator, how to use the simulator for pricing, how to improve the accuracy of results from the simulator, and finally look at some of the things that you could do when such a tool is available for you as a finance, mathematics, or computational finance professional. So that's an idea. So if you're ready, let's start. We'll start off with a simple sheet. The sheet that you see in front of you is the same sheet that we'd used earlier for estimating ND1, for building a more intuitive understanding of ND1, ND2, and the simulation process. And our objective is to build a sheet with a similar structure, a place where we can simulate the results based on inputs, a place where we can store the results, calculate the results, review the results, and a place where the actual estimation of premiums, where actual storage of each iteration and simulation happens. So a simulator, a storage slash calculator place, and a results warehouse. To do that, I've built a simple sheet. There we go, book 3. So let me just save this. I'll save this as Monte Carlo 1, and in order to save time, I just typed in basic inputs. These are the inputs to our model, and these include the spot price, the strike price, the volatility, the time to maturity, the risk-free rate, the number of steps that are used in the model, and delta t. I'm going to add two more terms: PV factor for t, big T, which is the whole time frame, and PV factor for delta t, which is the time step. Delta t, time step. So now in terms of inputs, the spot price is the price of the underlying. Let's set that at 10. The strike price is the strike at which both the call and the put contract would be exercised. Let's set that at 12. The volatility is at 30%. The time to maturity is 1 year, the risk-free rate is 10%, the number of steps are 10. So this is the number of steps in the price path, and we've left it to 10 because we want to keep the model simple so that you can follow what has been done and how it and then depending on your preferences, you can always extend it to multiple steps. Delta T is simply time to maturity here divided by the number of time steps. PV factor is EXP, continuous compounding, minus the risk-free rate R, see here, minus EXP minus R, the risk-free rate, times big T, or the time from between now and maturity. And PV factor of small t is the PV factor for the interval involved in each step, and is also EXP minus R. However, rather than using big T, we use small t or delta t. Right? So I now have most of the pieces available for me to start work on my simulator. I'm going to do a 10-step simulator, which means that I'm going to run simulation 10 times, and for that I need, let's say, a random set of random variables. If I go back to my equation that we used earlier, so you can see the equation that we want is S naught E raised to the power u minus half sigma square t into sigma under root t zt. The same equation that we'd used earlier in our understanding drift and diffusion session. Let me just paste it here. There we go. So the equation is here. Now, to build this model, we are going to need this piece, zt. And the primary problem that we will face is that this zt is not uniformly distributed but normally distributed. So the random number that Excel generates for us using the rand function, rand bracket open bracket close, this number, if you update it, will give you a number between 0 and 1. So a positive number between 0 and 1, indicating that each number in this range has an equally likely probability of occurring. This random number is of no use because the number that I need here is not uniformly distributed, is normally distributed. So I need to convert this random number into a normally distributed series, and I do that by applying the norm SINV transformation in Excel. So if you see, norm SINV probability basically assumes that the number that you're giving us, the number that's between 0 and 1, which is coming from the uniformly distributed random series, is actually a probability, and I can use the norm SINV number to use this as a seed for me to generate a normally distributed random number, which is here. So now you can see this 0.8717 corresponds to 1.131 in the normal world, 0.43 corresponds to minus 0.17, 0.8 corresponds to 0.86, and so on and so forth. So because I have 10 steps, I now need 10 numbers. So let's just extend this grid. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then we simply copy and paste the series that we have here. So both random and normally distributed numbers. And there we go. So now from this equation here, this piece is done. We now need to fill in these three pieces. Now if you see the series, you can see mu minus half sigma square, or r minus half sigma square, because we're assuming that we're earning the risk-free rate, is a constant. Sigma under root t is also a constant. It's zt where all the trouble happens. So let's break this up a little further. Let's say we have a certain component. We have a certain piece. This certain piece is r minus half sigma square. Then we have an uncertain piece. And this uncertain piece is sigma under root t zt, right? But within this uncertainty, the sigma under root t piece is actually constant. It's not going to move. It's the zt piece where the uncertainty comes in from. So if I simply calculate r minus half sigma square, so r, where is r? That's r, the risk-free rate. Let's anchor it by pressing F4 so that we get this cell locked. R minus half, so that's half, into sigma. Where's sigma? Sigma is here. Sigma squared raised to the power 2. So that's r minus half sigma squared times, remember, small t. So small t is delta t, which is this time step. So in a given time step, what you're saying is the price of the stock, the underlying stock, will move because of two parameters. One is certain, one is uncertain. The certain piece is 0.055. If I extend this from here to here, no, we have we locked it? Yeah, no, we've locked everything. We haven't locked D6. Let's lock D6. So F4. Now if I copy and paste it from here to here for the 10 steps, something is unlocked. Delta t is unlocked. So if you lock delta t, there you go. So now what you're saying is r minus half sigma square is a certain piece with respect to time that will certainly add to the value of the underlying as you move forward in time. Within the uncertain piece, the number you're looking for is sigma into square root of time, and time is delta t, and this number is 0.94868. Again, let's lock and anchor d6 and d4, sigma and delta t, and bring this down. So we haven't really hooked it or connected it with the randomness. Once we do, we'll see some interesting results. But for the time being, let's assume that this is a world in which there is no uncertainty. This randomness does not exist, and the equation that we're working off works with mu minus half sigma square t plus sigma under root t. Then the change in spot over this stage is simply exp this plus this. So both the certain piece and the uncertain piece. And if you were to go out and apply this, so your projected or simulated spot price calculated here would simply be, for the first one would be spot, current spot, into this return. If I were to extend this, that's my series, and in this case it will be the previous spot times this return, then again the previous spot times this return, and you would simply extend the series. Right. So now you have a set of simulated values. However, there is no simulation per se because we haven't hooked up and connected the randomness. But it will be interesting to see if I were to plot this as a series, what kind of a curve, what kind of a results do I get? And as we suspected, when you apply this without the randomness, the curve that you get is your exponential curve. It is a series that you expected to see. However, let's bring this friend here out of the way. However, if you connect and hook the randomness, and your randomness comes from this function zt here. So if you connect and hook the randomness, what happens to this curve and what happens to these prices? Where is the randomness coming from? It's coming in the uncertain piece. All we need to do now is simply plug in and link and connect to the normally distributed random variable or zt in the equation above. Are we ready? Let's do that. So that's 1, that's the first value, and we simply extend this to these cells, and lo and behold, the path has changed. Now, if I run the cycle, you have successfully gone ahead and simulated the value of a stock. So this underlying instrument, which is trading at 4, let me remove this, get it out of the way. Let's bring this back. Let's bring our friend chart back where we can see it. There we go. So we have our chart, and we have, let's get this out of the way. So there you go. So we have a chart and we have our series. So now what you've done is, quick review. What you've done is you started off with a set of input parameters given here. You then generated a uniformly distributed random number using the Excel function RAND. Then, because you needed zt, which is a normally distributed random number, you applied the norm-s INV transform on it. Then you calculated the value of the certain piece, which is r minus half sigma square. Then you calculated the value of the uncertain piece, which is simply volatility times square root of time. However, you were a little cautious, and before you actually connected the series, you actually wanted to see what kind of numbers you would get without randomness, and that was the exponential curve. Then you calculated the change in spot from one period to the next, and finally you linked everything together to get your simulated spot, which was simply st is s0 times the change in spot that has been calculated here. So at the end of this exercise, we actually have a simulated path that goes from 10.28 to 14.89. We plug in 1 to update this path to see what kind of results and numbers we get. Because I'm recording this session, I have to use this technique. If you're doing this in real life on your side, all you need to do is press F9 and the sheet will get updated. I'm just trying to create some space to see what kind of numbers we get. Now, 3 questions. What's the average spot? So the average spot is simply average of this path. What's the maximum? The maximum is simply max of this path. What's the minimum? The minimum is also min of this path, right? These are 3 numbers that we would use later on in the work that we do. For now, I only need one more piece, and that piece is ST, the terminal value of ST. What is the final value of ST? This is the value of ST that this model suggests, this simulator suggests, would be in place at maturity. This is the same value that we use for our work when we calculate the payoff of a call and a put option. So ST from our model is the value in the last, there you go, last simulation. Last step in the path, 9.8796. That's the value of ST. That's the value that we want. Okay. Now let me do the minimum and maximum. Let me move them here. And let's do them. Let's calculate them for both this piece. We'll see why I've done this calculation. What I want to see is that when we see large numbers, when we see very, very large numbers, what kind of numbers are we seeing in this range, and where does that correspond to, as well as what kind of probabilities are we seeing with respect to those numbers. Okay, so now that I have ST, what can I do? If I have ST, I first need to calculate the call payoff. What is the call payoff? If you remember, the equation is max of ST minus X comma 0. So we apply max of ST, there's ST, minus X. X is the strike price, there's strike, comma 0, bracket close. If you close this, that's the value of a call payoff. What's the value of a put payoff? The value of a put payoff is the other way around. It's max again, but rather than ST, we have X minus ST. So X minus ST, there you go, comma 0. So that's the value of a put contract. So we now have a call payoff and a put payoff, two elements. The only thing that we need to do to convert these values into premiums is to remember that these payoffs are at the point of terminal of ST of terminal S or maturity, which means that they're a year down the road. So we just need to calculate the call premium, we just need to discount it. To calculate the put premium, we just need to discount it, and we discount it using discount factor for big T. So call payoff times the discount factor for big T gives me premium for a call. Put payoff times discount factor for big T gives me the premium for a put option, right? So now I have most of the pieces necessary for me to move on to the next stage, and the next stage is to store the results. So very quickly, quick review: inputs, models, simulated path, ST, call payoff, put payoff, call premium, put premium. I now have all the pieces I need to move on to the next stage, which is to use the Monte Carlo simulator to estimate the value of the call option. Now, you have actually 2 or 3 choices. The first choice is, the way that this is supposed to work is, let's say I pick results. So let's store results here. Let me reduce the size of the sheet so that we have more space to work with. Let me move this here. So let's get this out of the way. There we go. Alright, so now what I want to do is I want to store results 1, 2, 3, 4, and 5. I want to store results, and when I want to store these results, what I want to do is I want to store what results? I want to store ST. I want to store, so let's call this ST greater than, so this is ST. Let's store whether ST is greater than X. I also want to store the value of the call contract, and I want to store the value of the put. Okay. So these are the 4 things that I want to store, and right now they are here. So I get ST. Is ST greater than X? We don't know because we don't have a logical test. Let's put in a simple logical test. ST is greater than X, and this logical test will help us track or calculate the value of ND2 when the time comes to calculate it. And this logical test is simply, if ST, there's ST, is greater than X, there's X or the strike price, then you give me 1, so ST is greater than X, or you give me 0, and ST is not greater than X. ST is 4.8, ST greater than X is 0. ST is 11.0892, ST is still not greater than X. 13.13, there you go, bingo. ST is now greater than X, right? Alright, so So that's the logical test that I want to track. So let's hook this here. That's my logical test. And then value for call. Value of a call premium is here, 3.92. Value of a put is 4.2783. There we go. So now, one way of doing this is that, I put in this value here, and I now manually store all of these results. So I have 7.4233 and 4.1412. 7.4233 will change the results to 4.1412. It gets complicated very, very quickly. Now the result is 9.6292. Everything else is 0, and I get 2.1452. So I need to put a 0 here, 0 here, and 0 here, and 0 here for the first iteration. Then for the third, it's 13.2406, and the value of the call is 1.12, and this is also 1, and this is 0. For the fourth instance, it's 8.4753. The value of the put is 3.1893, 3.181893, and this is 0, and this is 0. And the fifth instance, it's 8.5029 and 3.1643, 3.1643, right? And this is 0, and this is 0. So now what I've done is I've actually stored the results for 5 simulations, and as you can see, this is a very, very painful exercise. If I tell you that you have to run 10,000 simulations, it will be a very, very, very long time before we get done with this session. So there must be a faster way, there's a smarter way, and the good news is that there is a smarter way. What you can do is you can use the Excel data table functionality to trick Excel in storing these results for you, and we'll quickly see how that gets done. But before I do that, in essence what you would do from a simulation point of view is that now that you have these results, these 5 results, the actual value that you are going to use in your calculation process is simply the average of these numbers. And if I look through these numbers, what I'm seeing is I'm saying the expected value of ST based on these results that I have here in front of me is 9.45. The probability that ST would be greater than X is 0.2. Value of a call is 0.22. Value of a put is about 2.53. Right? That's what we've done. Now, if I were to do this faster and simpler, let's say I don't want to do 5 iterations, I want to do 10 iterations. So I extend this from 10 to, there you go, that's 10. And now what I'm going to do is I'm going to trick Excel into calculating and storing these numbers for me. And how I do that is simply I take this grid. So I've selected all the cells that I've put it here, and I have this data table here. My first step is to go to data. Next step is to click on what if analysis, then click on data table. I get a column input cell, I get row and column input cell, I pick column input cell, and I pick any blank cell on this sheet that is blank. I press OK, and like magic you will see that this grid and table will get populated. Excel will actually do all the hard work that we just done with our own hands earlier for you without any charge. There you go. So let me just clean this up and format this properly. So comma, it's fine. Now what you've really done is you calculated or run 10 simulations, and for each of these simulations you've stored the value of ST, stored the value of ST greater than X, stored the value of a call premium, stored the value of a put premium, and after running the simulation you can see that your results are slightly different. So there's now 40% chance that ST is greater than X, the call premium is 0.44, the put premium is 1.72. If you update the sheet again, numbers have changed. Again, numbers have changed. So these are your results. Okay. Alright. Now the primary problem here is that 11.17. So what I'm going to track is value of a call and value of a put. I want to see how much these results vary as I move forward in time. As I move forward in time, this is 1. So what I'm doing is I'm pressing 1 every time so that my sheet, my model, my numbers, and this table gets updated. In real life, if you're working on Excel, all you need to do is press F9. Because of the recording tool that I'm using, the F9 function is already spoken for, and I can't call it from Excel. If I stop the recording tool, I can call it, but then I will not be able to record it. So I've got a quick fix, and that quick fix is I simply plug in the number 1 or any number, and whenever I press enter or update, the cell update gets triggered and the result that I want gets happened. So here what we're really doing is that Excel takes this one and plugs it into the empty cell that you've identified. When it puts that into the empty cell that you've identified, this gets updated. More importantly, this sheet, this random number that you have here, this gets updated. The price path gets updated. These results get updated. Then because you've linked these cells, so each of these cells refers to the appropriate cell here. Because you've linked these cells, what Excel does is that it calculates all the values that are here in these cells and stores them here. Then it picks the number 2, does the blank cell. When it does the blank cell effectively does what I'm doing here. When I plug 1, it triggers the cell update, updates the random numbers, update the price path, update the payoffs and the premiums, store them. Then 3, 4, 5, 6, 7, 8, 9, 10, right? And every time I press F1 here, this cycle gets run. This entire cycle, this 10 simulation cycle gets run end to end. Model, random numbers, price path, calculations, store results, calculate values. Right? That's the sequence. That's the cycle. Now the only problem that I see here, and I think you can possibly see it also, the problem that we see here is much better. Now the problem that we see here is that if I press 1 here, look at the numbers, look at the value of the call and the value of the put. So one iteration 0.43 2.15, second iteration 0.38 1.7, third iteration 0.33 1.84, fourth iteration 0 and 1.7. So there's a lot of variance. And then also if you track ST is greater than X, this cell here, column B, 1 iteration, 2 iteration, 3 iteration, 4 iteration, 5 iteration. So switching between 20 and 40. So there is a lot of movement here, and I think my worry in my my worry is that these results are not stable. There's a lot of movement. Is the answer 0.73 for a put, or $1 for a call, or is it 0.7, or is it 1.3, or is it 2.2, or is it 3.48? What is the answer? What is the right answer? How do I find out? The only way that you can increase the accuracy of your model or bring stability to your model is by doing more iterations. That's the primary check. So what we need to do now is to see if we can improve the model by adding these additional iterations. We will do that immediately after the break, after we come back from